I'm Yusebi.
I'm Daniel.
I'm Andres.
I'm Emily.
And we're going to be talking about how to build a mini-sun on Earth.
Otherwise known as extracting energy through nuclear fusion. Alright, so as you may know, our goal is to create a mini-sun on Earth. And the way we're going to go about that is through nuclear fusion. Here we have the equation in which we have hydrogen 2 plus hydrogen 3 makes helium 4, a neutron, and 14.1 mega electron volts. That's a lot of energy. And the way that works is in deep space, there are these huge clouds of hydrogen gas. And the way gases normally work is they bounce each other off elastically. But because the gravity is so intense and there's so much pressure on these gas particles that they can't avoid colliding and fusing together. Now when they collide, they break the Coulomb barrier from being on the repulsive side to the attractive side, letting the strong force take over and allowing them to fuse together.
Now, we know what we need to do. The question remains, how do we go about doing it? Now, obviously, given the extreme temperatures and energies necessary to produce a fusion reaction, confinement is one of the biggest issues currently facing scientists. Now, fortunately enough, there are several methods scientists are currently using to confine these reactions in the lab. The first of these is called magnetic confinement. Now, if you know anything about plasmas, you know they are an ionized gas, meaning they're extremely good at conducting electricity. This property allows scientists to confine them using magnetic fields through something called the Lorentz force. Now, unfortunately, the Lorentz force only acts perpendicularly to the direction of magnetic field lines, meaning that if a plasma is combined linearly, a great deal of it will be allowed to escape. However, scientists have worked around this issue by confining plasmas in a shape called a toroid. Now, the curved donut shape of the toroid allows the magnetic field lines to bend in on themselves, minimizing the amount of plasma that escapes. Now, the second, more efficient method currently that is being used is called inertial confinement. Now, this is done by taking a compressed pellet of fuel, generally hydrogen, tritium, deuterium, and heating it with an extreme number of lasers. Now, this heats the outside of the pellet, producing the temperatures needed for fusion, and at the same time, the extreme expansion on the outside compresses the inside, sending shockwaves to the center and creating the extremely dense, high-temperature environment necessary for a fusion reaction to occur.
Now that we know how we're going to design the reactor, we need to know what materials we're going to use. The plasma-facing component that makes up the first wall needs to be able to withstand a neutron flux of about 100 times that in pressurized water reactors, and it needs to do so long enough to be economically viable. It also needs to allow the passage of large heat flux, and it needs to withstand intense and fluctuating magnetic fields. In addition, it cannot become so radioactive that it produces too much radioactive waste when it gets replaced or when the plant gets decommissioned, and it cannot contaminate the plasma too much. There are two possibilities for materials used in fusion reactors, those with low proton number and those with high proton number. In regards to low proton number, you're usually looking at graphite, although in some cases beryllium. The main disadvantage of graphite is that it has a lot of sputtering, and many atoms get ejected from the material when it's bombarded by energized particles. When these atoms return and get redeposited, they also deposit tritium into the walls, and this can build up, and that's first and foremost wasteful because the tritium is not being used in the reaction anymore, and it's also potentially dangerous in case of an accident. The high proton number material that's most commonly used is tungsten. The main advantage of tungsten is that it does not have this sputtering problem, and so very low amounts of tritium get deposited back into the walls. Although it has the disadvantage that tungsten impurities in the plasma are much more damaging than carbon impurities in the plasma. Now, these materials have not been tested very much, but the International Fusion Materials Irradiation Facility is going to use an accelerator-based neutron source to test materials for fusion reactors. In addition, here at U of I, we have a plasma cannon that's used to test materials for fusion reactors.
As many of you probably know, this concept of mini-sun on Earth is pretty difficult to achieve, even though significant progress has been made. The National Ignition Facility in California blasts tiny capsules of deuterium-tritium with 192 laser beams in order to achieve that brief fusion reaction.
Just in late September, there was an experiment conducted in which the amount of energy released from the reaction exceeded the amount of energy absorbed by the fuel. Even though this does not yet qualify as an ignition, which is a self-sustaining reaction in which the energy input by the lasers is less than the energy output, it still is a scientific break-even point. Another project underway is the ITER project, or International Thermonuclear Experimental Reactor. And pretty much their goal is to achieve this formula. Q is greater than or equal to 10, where Q is the ratio of fusion power to input power. And by this, they want to achieve a reactor in which the energy released by the reactor is 10 times the input power. So that is almost like a mini sun on Earth. Another major problem in this concept is the confinement of plasma. In stars, the mass of hydrogen is so large that its own gravity keeps helium and hydrogen confined to a small area in the center, and the temperature in the millions of degrees. Essentially, plasma is confined forever, and protons cannot leave and take their energy with them. Hydrogen fuses into helium, and energy is released. But this is not so easy in the lab. At Sandia National Laboratories in New Mexico, they are testing a method called magnetized inertial fusion, in which coils are used to generate a magnetic field in order to confine the plasma. The metal cylinder in each of the coils is lined with an inner coating with deuterium tritium. This liner is then preheated with lasers and then hit with a current of millions of amperes. The current vaporizes the liner, but before it does so, it creates a magnetic field, an outer magnetic field that is very strong. It has a magnetic force that is so crushing that it is just enough to keep deuterium and hydrogen confined long enough to fuse. And then this releases one neutron and energy. Thank you, and that's the end of the presentation.